I'm really excited to be able to introduce Michael Manga as our Colloquium speaker. Michael is a professor and chair of Earth and Planetary Sciences at Berkeley University. He's also received numerous awards for his research, including being a fellow of AAAS and the National Academy and AGU and GSA and a MacArthur Genius Grant. He started his academic journey with a master's in engineering and a PhD in Earth and Planetary Sciences, both from Harvard University, before moving to be a Miller postdoc fellow at UC Berkeley. And then he spent a few years as an assistant professor at the University of Oregon before moving back to Berkeley in 2001. So Michael's an expert in the application of fluid mechanics to all kinds of geological problems. And I was thinking earlier, like as I put together people's introductions, I quite often end up saying, oh, the speaker's worked on a wide variety of problems. But I think Michael gets the prize on this in kind of scientific versatility. So he's worked on all kinds of things that I would have thought were quite disparate, like mantle plumes and bubbles and crystals in magma and the effects of large woody debris on stream channels and the internal structure of Europa and possible links between earthquakes and eruption triggering. And we learned just today that he's working on melt inclusions now and on beach sand. So it turns out fluid mechanics crops up in all kinds of scenarios. And today, Michael's talk is about submarine volcanic eruptions. So thank you very much, Michael, and we hope to see you in person soon.
Yeah, thanks, Megan. You know, our department calls itself the Department of Earth and Planetary Science without an S at the end. And we take great pride in that. And it's a complicated history behind that name, but we collectively decided there's one science behind studying the Earth and planets. And so we are the Department of Earth and Planetary Science without an S. And thanks so much for giving me the chance to come and share some of our ongoing and recent work. And hopefully it'll be interesting enough. I'll have the chance to come back some other day and maybe in person. I think it's been more than a decade since I've given a talk at the University of Maryland. Please put any questions you have in the chat, or at least simple ones, and I'll try and pay attention to them and I can try and address them real time as we go. And if I'm ignoring you, just interrupt and yell out. So, you know, one of the key questions in volcanoes science is understanding why volcanoes erupt in so many different ways. For example, Mount St. Helens erupted explosively on the left in 1980, sending ash high into the atmosphere to be dispersed over a broad area. And more recently, starting in 2004, Mount St. Helens started erupting again, essentially the same magma, but a style we call effusive, to make the lava dome, the little bump you see here in the middle. So why does magma erupt? Magma at depth contains dissolved gases or volatiles, mostly water, but also CO2 and other gases. And as this magma is rising, the pressure decreases and the solubility of these gases will decrease. And so they come out of solution to form bubbles. And as the magma continues to rise, the pressure continues to decrease. So these bubbles are going to grow. And eventually, when there's enough bubbles in the magma goes through a process we call fragmentation. And here there's a change in topology of the magma. We go from a continuous melt phase shown in red in the cartoon to discrete pieces of bubbly magma surrounded by continuous gas. And these are the small pieces of magma that erupt explosively. And so presumably the transition between an explosive eruption and an effusive one is the loss of this process called fragmentation. So today and so whether or not magma fragments ultimately is going to have a large effect on the eruption styles that we see. And so today what we're going to be doing is looking at eruptions under the ocean, both how they erupt and then why they erupt in the different ways they do. So on July 18, 2012, the Havre submarine volcano in the Kermadec Arc, north of New Zealand, erupted more than 1 cubic kilometer of pumice, creating a raft of floating rock. And you might be able to see the raft on the right. It's this gray streak running across the screen where the vent was located under the green dot saying pumice source. So briefly, pumice is a volcanic rock full of bubbles. And over the coming years after this eruption, the pumice was transported throughout the southern oceans and washed up on beaches. And I'm going to do a quick demo. I'm gonna have to, the multiple screens I have to watch. So this is a piece of pumice. What's special about this piece of pumice? Besides it being full of bubbles, maybe you can see the bubbles. There's something special about its shape.
It's rounded.
It's kind of rounded, and it's rounded because it's floating on the ocean surface, jostling against other pieces of pumice and getting abraded. Okay, this was picked up in New Zealand on the beach. And I have a container full of water. And if I put the pumice on the water, you can see it floats, right? And of course, that's how it gets transported across the ocean. And amazingly, despite being the largest submarine eruption in at least 400 years, the eruption was not known to scientists for a couple of weeks when a passenger in a commercial airplane saw the raft and contacted a volcanologist at the University of Queensland in Australia. Well, in fact, most submarine eruptions are discovered by serendipity. The plot on the left from Adam Sewell is a plot of the cumulative number of submarine eruptions documented in the Global Volcanism Project database at the Smithsonian over the past couple decades. And from the slope of this line, you can see that it amounts to less than one eruption per year. Just for comparison, about 100 different volcanoes erupt on land every year. And so given that 85% of volcanic activity happens under the sea, we're probably aware of and are documenting maybe 1 out of 1,000 submarine eruptions, despite all the modern tools we have at our disposal to monitor the Earth. The 2017 National Academy's Erupt report identified 2 scientific grand challenges in volcano science, one of which was to quantify the life cycles of volcanoes globally to overcome our biased understanding. And I would argue that volcanoes under the sea are poorly documented, and their life cycle and the processes that control their eruptions, as well as the fate of those erupted materials, also remain poorly understood. So the map on the left shows the dispersal of the raft over the first few days, with the brown patch being the position of the raft after 1 day, already covering more than 400 square kilometers of the ocean. And these rafts are more than curiosities. You can see on the right that they're colonized by life, and they transport that life great distances. And as the pumice floats, it abrades, right, to make that nice rounded clast you saw earlier. And this releases ash and nutrients into the ocean, fertilizing the ocean. Well, there's several open questions about this eruption and submarine eruptions more generally. What was the volume that erupted? What was the eruption rate? We care about eruption rate because it controls the style of volcanic eruption. How is it that this pumice, the rock full of bubbles, got up to the ocean surface from the depth of the vent? The vent was at 900 meters below the ocean surface. And what do deposits from these eruptions look like? And the challenge to answering all these questions is that what we had was observations from of the ocean surface, not from the seafloor. And Ved is asking an excellent question. Was there a seismic signal associated with the eruption? This eruption was not forecast based on seismicity. And it took 2 weeks to identify that the eruption happened because the biggest earthquake associated with this eruption was a magnitude 5.1. And there are magnitude 5.1 earthquakes that happen all the time in the Kermadec Arc. After the fact, we can go back and identify earthquakes. Their location is quite poorly constrained. The uncertainty is probably, I would say, more than 20 kilometers because there aren't any seismic stations nearby. But I can dig up what the seismicity looks like at some point for you, Ved. Okay, well, to answer these questions, in March 2015, the MESH expedition sampled and mapped the Havre volcano. And MESH is an acronym for Mapping, Exploration, and Sampling at Havre. And there were 2 components. First, the remotely operated vehicle Jason on the left collected samples, images, and made a variety of other types of measurements. And the autonomous underwater vehicle Sentry on the right mapped 56 square kilometers of the seafloor with meter scale spatial resolution. And there's a variety of other coring and geophysical measurements that I will not talk about today. Well, the new bathymetric data revealed that the eruption that created that raft of floating pumice was accompanied by the effusion of 14 new lava flows and lava domes, colored here in pinkish, and they're labeled, and their total volume is about 0.3 cubic kilometers of lava. One distinctive feature of the deposit we see on the seafloor is a field of giant pieces of pumice that we call giant pumice with diameters that exceed 1 meter. A couple examples of photographs are shown on the bottom. The background image is the bathymetric map made from the autonomous underwater vehicle Sentry. And the bumps that show up in the topographic map are these giant pieces of pumice. And some of them can get quite large. And I should point out that volcanoes on land do not erupt pieces of pumice that are this big. These giant pieces of pumice were dispersed down current from the inferred location of a vent, which lies underneath this dome here in the background. And we know this from stratigraphic relationships. And interestingly, the mean size of these pieces of pumice increases as we move away from the vent, which is the opposite of what we would see on land, where particles systematically get smaller with transport distance, except for volcanic bombs. Okay, I'm going to I'll give you run a short video now just to give you a sense of what we did. So we obtained high-resolution bathymetric map of the caldera that allowed us to image and see these lava flows, as well as other mass wasting events, in fact. And this is the remotely operated vehicle, Jason, being lowered to the seafloor. To collect and return samples, including what you'll see next, one of these pieces of giant pumice. For scale, it's about 2 meters across the front of Jason. So this piece of pumice is 1.5 meters across. And with these return samples, we can make a variety of different measurements. Okay, well, given that we were able to go to the seafloor, we do know something now about the history of this eruption. We know that the eruption formed the raft and the giant pumice, and then these lava domes were extruded. We can get the volume that erupted from the mapping and the size of the raft. From satellite images, we can get a constraint on the eruption rate. And from the imaging, we know what the deposits from these eruptions look like. To answer the last two questions, the ones in red, how did the magma erupt and how did the pumice get to the ocean surface? We're going to have to rely on measurements we make on the erupted rocks combined with some modeling. So I did want to return to this picture I showed you earlier. Why do volcanoes erupt in so many different ways? Right? Because you saw that we made lava domes. We also made this floating pumice. Presumably this fragmentation process happened to make the pumice we see at the ocean surface. So let's talk a little bit more about how it is that magma fragments. And for a liquid to be able to flow, the molecules that make it up have to be able to rearrange their configuration as fast as you're trying to deform it. If not, the liquid will not behave like the fluid will not behave like a liquid. It will become brittle and it can break. And we can do another little demonstration, something that you're probably familiar with. I have a ball of silly putty. And you know that if you pull on silly putty slowly, if the strain rate or deformation rate is low, it stretches. Right? So the silly putty is ductile. And if I pull fast enough, I can break it into two pieces. If the deformation rate is high enough, it can become brittle and it can break. And this is the primary mechanism through which magmas fragment to give rise to explosive eruptions. And we do know that the deformation rate needed to fragment magma is inversely proportional to the viscosity. So one way, of course, to prevent explosive eruption is to keep the magma from deforming too fast. And what drives magmas to the surface are the dissolved volatiles that make bubbles. The bubbles provide buoyancy, they expand the magma, causing it to accelerate through the conduit. So another process that is important besides fragmentation is the loss of gases during ascent, indicated by the blue arrows here that I'll call outgassing. And it is the interplay between making bubbles, magma ascent, outgassing, and fragmentation that ultimately gives rise to the diversity of eruption styles we see. So we know quite a bit about this eruption now from a variety of measurements we can make either on the erupted materials or from other observations. And so I'm going to list some of the features of this eruption that we know. I'm not going to take you through the details of how we know these, but if you have questions, either put them in the chat or we can talk later. We know the eruption rate from satellite measurements. We know the temperature of the melt from geochemical measurements. We know how much water was dissolved in the melt to form bubbles from melt inclusions. We can compute the viscosity of the melt. We know the depth at which magma was stored in the subsurface before eruption. We know the pressure at the vent because we know where the vent was. And we know something about the texture of the magmas that erupted. Two critical things that we don't know is, first, what is the process that gave rise to fragmentation to break up the magma? And second, what is the geometry of the pathways that allowed this magma to ascend up to the surface? And we're going to answer these two questions now using computer simulations of magma ascent and eruption. And so first we'll look at a model for magma ascent in a conduit. And we're going to solve for the coupled two-phase flow of gas and melt, allowing for the possibility that gas escapes from the rising magma as it's ascending up to the surface. And we're going to compute the key variables that change as magma rises. So the pressure, the speed of each phase, the properties of the magma, like the viscosity, the deformation rate, and the properties of the bubbles. Okay. And so I'm going to show you one example of what happens to magma as it ascends through a conduit. And then I'm going to try and generalize what we learn. So I'm plotting a variety of measurements as a function of depth inside this conduit, connecting the seafloor to where the magma is stored deeper down. And I'm only showing you the upper 4 kilometers. 0 would be the seafloor going down the vertical axis. First on the left is pressure. As magma rises, pressure obviously decreases. As pressure decreases, the solubility of gases decreases. And you can see on the right that as the solubility of gases decreases, gas goes into making bubbles, the volume fraction of gas increases, and at the vent reaches about 80%, which is the same volume fraction of gas we see in the erupted magmas. As something I did not point out earlier, adding dissolved water to silicate melts greatly lowers the viscosity. And so as the water goes from being dissolved in the melt to making bubbles, the viscosity of the melt increases, in this case by about 2 orders of magnitude. And now the most important quantity we keep track of is how fast is the magma deforming, and is it deforming fast enough to break the magma? And this is what's plotted in the second plot. The deformation rate compared to that needed to break the magma. And you can see, although the numbers are very small, this number is always much less than 1. And so the magma is not deforming fast enough to break. And the reason for this is in fact controlled by erupting under the ocean. If we look at the third panel, you can see the viscosity is increasing quite a bit as the magma is ascending because we're losing water. But because of the high pressure enabled by the ocean, we don't lose that much water. And so there's enough water dissolved in the melt, the viscosity stays relatively low, and the melt is not able to fragment. There's obviously a lot of uncertainty in the geometry of the pathways through which the magma ascends and the physical processes here. But even if we change key parameters by more than an order of magnitude, deformation rates are never big enough to break the magma because it's deforming too fast. So first question, can magma fragment in the conduit? And the answer is no. So what does this mean? It means that we're squeezing or extruding bubbly magma into the ocean. If you have 80% bubbles, you're less dense than the ocean. So we are extruding buoyant, bubbly magma into the ocean, and it's hot. And if you've ever taken a hot glass or something too hot and tossed it into water, you know that it can shatter and break. And presumably the same process will happen to this glass that's extruding into the ocean. If fragments that form are big enough, they will be able to float up through the ocean column faster than they're being squeezed into the ocean, which would allow them to separate from the magma being extruded into the ocean. So we can compute how big a fragment needs to be able to float away from that extruded magma. It depends on how big they are, their density, and a drag coefficient. And this number is that fragments need to be bigger than about 1 meter for them to float faster than magmas coming into the ocean. Okay, so any fragment bigger than about 1 meter is able to float away from the extruding magma. And these are bubbly pieces of magma. And you can imagine if you're hot and you're full of bubbles, that as you cool into the ocean, the gases are going to contract. The gas is mostly water vapor. And as the gases contract and the water vapor condenses, it's going to suck in ocean water. And if you suck in ocean water to something bubbly, you get more dense. And so now we need to answer the question, will these bubbly magmas suck in enough water before they reach the ocean surface that they sink? Okay. So what we need to do then is figure out, well, how fast does a hot piece of magma suck in water? And we developed theoretical models for how fragments cool and ingest water. We also do lab experiments to test our theoretical models. And so what I'm plotting here on the vertical axis is how long it takes for a piece of pumice to float up to the ocean surface as a function of their size for different volume fractions of bubbles inside the magma. And what erupts on the ocean floor is typically about 80% gas. And these curves only begin if the piece of pumice is able to float up to the ocean surface before they ingest enough water. And so what is the answer? If you're bigger than about a meter, you can float up to the ocean surface before you ingest enough water to sink. And maybe a bit about the physics, since I'm not showing you any of the equations and the solutions. The primary rate limiting step on ingesting water to become more dense is the ability to lose heat to the surroundings, because losing heat enables water to condense. Okay, so if you're big enough, you can float up to the ocean surface and exchange water vapor with the surroundings. And it's an interesting question. Can you reach a level of neutral buoyancy? And I think, so there is some point when a piece of pumice is rising through the ocean when you become as dense as the ocean water. At that point, though, you're still warmer than the ocean. And so as that piece of pumice continues to cool, it's going to continue to ingest water and eventually sink. And so pieces of pumice will rise through the ocean, reach some level of neutral buoyancy. They will get more dense and they'll sink back to the ocean surface. But in fact, this explains why bigger pieces of pumice get transported further from the vent. The bigger you are, the longer it takes to cool, the longer it takes to ingest water to become denser than the ocean and to sink. And so bigger pieces of pumice take longer to saturate, and hence they're transported greater distances. And the model equations in the model that I referred to in a paper will allow us to compute exactly how long that takes. Okay, so now we have pieces of bubbly magma floating on the ocean surface. And two interesting questions. Well, how long will they float on the ocean? But it turns out that after floating for a while, pieces of pumice can still ingest enough water that they become more dense than the ocean and they will sink. And for those of you who have looked at IODP cores, you may have seen pieces of pumice randomly scattered inside the core. It's a quite common observation because as these pieces of pumice are transported throughout the oceans, they will eventually sink and be deposited far away from their host volcano. Okay, well, to answer these two questions, we did a number of different lab experiments. First, we take pieces of pumice, we heat them up to a range of different temperatures, and we put them in water, and we look at what happens to the water. How does the water enter the piece of pumice? Okay, and so here I'm going to, and then we image where the water is using X-ray computed microtomography that allows us to image what is the glass in white in these images, what is gas in black, and what is liquid water in blue. So pictured on the right is a two-dimensional slice through these pieces of pumice. The one in the middle shows a piece of pumice collected from the Raft. The one on the right, giant pumice collected from the ocean bottom. And both of these pieces of rock were heated up and then placed into water. And then we see where the water goes. And you can see the image in the middle. As water enters the rock, it traps vapor bubbles. Whereas in the giant pumice on the right, the water very efficiently displaces all the gas. And so our conclusion is that if you're a piece of pumice and you efficiently ingest water, you sink. And if you don't, you float. And so when we collect pieces of pumice from the Raft, they have a texture that traps gas. The ones that we collect from the seafloor have a texture that allowed efficient ingestion of water. And I think I'm going to skip this, but maybe I'll just point out that in passing, that too many graphs, that there is also a subset of bubbles that we see inside volcanic rocks that are completely isolated. And those bubbles will never be able to fill up with water. And that can allow pieces of pumice to float indefinitely. And Ved is asking, of course, the key question, what ultimately controls the texture? Inside a volcanic conduit, as magma is ascending, the magma adjacent to the conduit walls is moving at very low velocity or zero velocity. So because of the velocity gradients, there are different deformation histories that lead to different bubble connectivities. And it's that topology of the interconnection between bubbles that controls how water infiltrates. And we see that reflected in the textures of rocks. In some of the pieces of pumice, we see nice elongated bubbles, and others we see nice spherical bubbles. And I'll show you some images later, and we can see some of these differences in texture. So the second of these questions was, how long will pumice float? And so once again, we do lab experiments. We take pieces of pumice, we put them in water, and we wait until they sink. And so plotted on the vertical axis is how long it takes for pieces of pumice to float as a function of their size on the horizontal axis. The black points are pieces of pumice collected from the seafloor. Ones we collected from the raft are the squares. And there's a subset there that says still floating. And these are the simplest experiments ever. I'm not sure if this is showing up. So those are the pieces of pumice that are still floating. They're sitting in little vials, and maybe you can see that they're still floating after, now I guess it's almost 5 years. And those pieces of pumice are floating because they do have some trapped isolated bubbles. Okay, so why is it that some pieces of pumice eventually sink? That gray bar that you're looking at shows the time scale for gas to diffuse from a bubble to the edge of the clast floating on the ocean surface. And so there is time, if you wait long enough, gas can diffuse from bubbles through the water to be lost to the surrounding atmosphere. And then eventually become more dense, and then you sink. But this does allow pieces of pumice to float for longer than years. Okay, I think I got all the. So the question about the crystal content in these samples, the primary control on density is going to be the volume fraction of bubbles, because basically bubbles have no density. Crystals and melt have very similar densities. So long as the volume fraction of bubbles, the vesicularity is bigger than 56%, the pumice that enters the ocean will be less dense than the ocean water. So that will be ultimately the critical number. So why does pumice float? We argue it's because you trap non-condensable gases. And because of outward diffusion of trapped gases, eventually pumice can become more dense in the ocean to eventually sink. Let's see, I'm paying attention to the time. So remember that earlier on when we talked about Mount St. Helens, that we said Mount St. Helens erupted explosively, it then erupted effusively to make a lava dome. And here at the Submarine Havre volcano, we began with a raft-forming eruption made of fragments of pumice that transitioned to an effusive eruption to make those 14 lava flows and lava domes. So presumably this was the result of fragmentation not happening or losing enough gas that the magma that erupted was not less dense than the ocean. And I intentionally actually picked the Mount St. Helens comparison here because the eruption rate for the Havre raft forming stage of the eruption was the same as the Plinian eruption at Mount St. Helens. And the eruption rate that made the lava domes was comparable to the effusion rate for the dome forming eruptions at Mount St. Helens as well. Well, in fact, if we look at the texture of the magmas that erupted, we do see evidence for gas loss during ascent. The picture on the left is a piece of pumice from the raft. And you can see now nice sub-rounded bubbles as these bubbles grew and expanded. You can see that they also connected, and this is creating the permeability that allows water to enter. Whereas on the right, you can see the texture of what we collect from the dome. And these bubbles are irregularly shaped. And these are presumably caused by the collapse of bubbles as gas is being lost to the surroundings. Also shown on the right are these little areas highlighted in blue. This is the mineral cristobalite, which is formed by vapor phase deposition. So another piece of evidence that a lot of gas was flowing through this magma into the surrounding rocks. And Richard Ash is asking, for these rocks that are floating, is it gas diffusing out and water diffusing in? If gas is diffusing out, the volume of the bubbles are shrinking, and so water is flowing back in. Okay, so in these simulations of magma rising through the conduit, we are keeping track of what the gas is doing, and the gas can move with respect to the liquid and be lost to the surrounding rocks. And so I think this might be the last graph I'll be showing you. Again, I'm going to show you a variety of properties of the magma rising in the conduit, depth below the vent on the vertical axis. And we have two conduits, a thin one in red, a wider one in blue. And in this case, I'm picking a single eruption rate. And to force magma through a small conduit, you need a big pressure. And then when you have a big pressure inside the conduit, that pressure difference between the conduit and the surroundings is going to force gas into the surroundings. And so what's plotted in the third panel is the flux of gas into the surroundings as the magma is rising. And the bigger the pressure difference is, the faster the gas is being lost. And so this enables gas to be lost during ascent. And earlier, for high mass eruption rates, we were erupting magma with a volume fraction of bubbles about 80%. Here we can erupt magma that has, say, 10, 20, 30% bubbles, right? Provided it's going slow enough or the conduit is small enough that we can lose gas during ascent. So I'm going to try and do my best to try and explain this very complicated busy plot on the right that's going to try and summarize all the processes that occur as magma is rising up to the surface. Okay, so we have two sets of curves. There's some in blue and some in red. These correspond to magma rising through conduits of different sizes, either a 30-meter diameter conduit or a smaller one in red. On the horizontal axis is the mass eruption rate. And what's plotted on the vertical axis is the gas volume fraction when the magma enters the ocean, the vesicularity. The horizontal green line shows the vesicularity needed for the pumice to be able to float, big enough vesicularity, or to be more dense in the ocean. I call this sinking. And last, the little colors you see for each of these points, actually that's not last, second last, is the overpressure in the magma storage region needed to get that mass eruption rate. And then there's little numbers next to these curves. This is the logarithm base 10 of the permeability of the country rock. 10 to the minus 14, 10 to the minus 13. I think there's 10 to the minus 12 on there. These are typical permeabilities of crustal rocks. Okay, so early on when the eruption begins, you expect the overpressure driving magma to the surface to be big, and we can get large mass eruption rates, these lightish colors, the yellowish colors. There's two blue areas on this curve, on this plot. The one labeled Raft are the conditions that characterize the raft forming eruption. And then there's an arrow that says dome. These are the conditions that characterize the dome forming eruption. Okay, and there's an arrow because we don't have great bounds on how long the eruption lasted. Okay, so early on, we can get large eruption rates because we have a large overpressure. We retain enough gas in the magma that we can erupt a vesicular magma that can float up to the ocean surface. As time goes on and we lose overpressure driving magma to the surface, the eruption rate decreases. We move right to left on these curves. We lose gas to the surrounding country rock, so we erupt a magma that has a lower vesicularity and possibly dense enough that it's no longer able to float, and it makes lava domes. And we can quantify how much gas is lost to the surroundings. So at the beginning, I listed a variety of different questions. And let me relist those questions and some answers. Did magma fragment in the conduit to make the fragments that we see in the raft? I argued the answer is no. Instead, buoyant magma was squeezed into the ocean, where it quenched in the ocean to make the fragments that floated up to the ocean surface. If these fragments are big enough, bigger than about a meter, they can reach the ocean surface. And if they trap enough gas, they float. How long does pumice float? If it traps enough gas or has isolated porosity, it can float for a long time. The ones in my office are still floating. And the transition to the effusive eruption is caused by gas loss during ascent, enabling a more dense magma to reach the ocean seafloor. And so I can summarize what we have learned on these two cartoons that do in fact have a lot of numbers based on a combination of observations and modeling. So early on, we erupt magma with a gas volume fraction of about 80% that can float up to the ocean surface, more than 1 cubic kilometer of floating pumice, and a smaller fraction sink to the seafloor to make the giant pumice you saw in those images. As the eruption rate decreased over time, more gas was lost to the surroundings. These, of course, are the fluids that make our hydrothermal deposits that we see at these volcanoes. And we erupt a magma more dense than the ocean to make the lava flows and lava domes. In the submarine realm, ocean depth really matters. I focused on the picture in the middle because we know the depth of the vent. If the ocean depth was greater than about 3 kilometers or so, the vesicularity of this magma would always have been low enough that the magma would be more dense than the ocean. And if the vent was shallow enough, deep, shallower than about 200 meters, in fact, the magma could have fragmented in the conduit. And this would have made an eruption style much more analogous to the Plinian eruptions we see on land. Okay, well, these kinds of pumice-forming eruptions are not exactly uncommon. This is an image taken in August, I guess it's just over a year ago now, of a raft encountered by a sailing vessel. And you can see that this raft of floating pumice stretches off to the horizon. Okay, this particular eruption happened in the Tonga Arc, so north of the Kermadec Arc, a little bit further north from the submarine eruption we were just talking about. The ocean depth here was quite a bit more shallow, just 200 meters below sea level. The eruption was also much smaller. That may have looked like a big raft, but this is 2 orders of magnitude less magma erupted. And because these sailing vessels entered the raft within a day of the eruption, we have a good sampling of pumice clasts before they were significantly abraded, and we also know what their initial sizes were. A few satellite images just to give you a sense of what these rafts look like. Satellite image in the upper, these orange bars are 2 kilometer scale bars for each image. And satellite images did capture the initial explosion, this underwater steam cloud you see in the little inset, and then the condensed water vapor cloud above the ocean surface. The other pictures show the raft, and you can see they have these intriguing wispy shapes. The yellow arrows in panel B in the upper right show abraded ash being lost into the ocean from the raft. Right, this is the ash that can fertilize the ocean. And jumping to the lower right, the green arrows show some of these floating rafts, and the yellow arrows show these rafts that have washed up on beaches. Okay. Well, we can use satellite images to track the raft over time. On the top, each of these colors show the position of the raft at 1-day increments with a 20 kilometer scale bar. The vent location is shown by the red triangle, and the bottom over the first 1 month time period with a 50 kilometer scale bar. And these images are useful for testing and calibrating oceanographic models and wind models to forecast the fate of this raft, as this pumice raft is carried by wind, currents, and waves. Shown here are some forecasts for the average particle concentration in blue at different points on the ocean surface over the first 2 years. Darker colors mean more pieces of pumice pass by that location. And in the lower right is the time it takes for pumice to reach a certain point on the ocean surface, going up to in yellow 2 years. And at the beginning of September of last year, pumice did in fact start washing up in the Great Barrier Reef off the coast of Australia, as forecast by these models. So briefly to wrap up, what next? Well, originally we were supposed to have 2 more cruises this fall in October and then November. And you can probably guess why they did not happen, at least on schedule. The first was to study the evolution of the hydrothermal systems supported by these submarine eruptions and the biological recovery of disturbed seafloor communities. And the second was to study deposits from the even larger caldera-forming eruptions, right? There were volcanic eruptions that made the caldera that you can see here. And the deposits from these eruptions, we hypothesize, are these features that look like waves of sediment extending off the flanks of the volcano. I have some white arrows pointing out these features that look like waves of sediment. And we hypothesize that these are produced by the submarine equivalent of what we call on land pyroclastic density currents or pyroclastic flows from the caldera forming eruptions. So just to wrap up, buoyant rhyolite was extruded into the ocean, and the eruption rate was large. It was similar to the Plinian eruption of Mount St. Helens in 1980, but the eruption was effusive. And I think I would argue there's no on-land equivalent of this type of eruption. We learned that the surface eruptions here provide only a partial record of the processes. The presence of a pumice raft, for example, suggests an explosive eruption, but I argued that this was fundamentally an effusive eruption. And so analogies to on-land eruptions are limiting because the processes in deep water can be fundamentally different. Here, for example, it's the high pressure of the ocean that suppresses fragmentation in the conduit. But at the same time, we argued that the ocean promoted fragmentation by quenching. And of course, the ocean also transports the vast majority of the magma that erupts, and it transports it far away from the vent. And so the deposits from these submarine eruptions are no longer preserved next to the volcano, as they are on land. And actually, for me, this was also another reminder of the value of international, interdisciplinary collaboration. So far, for example, 5 different PhDs have been completed based on data and samples from this expedition. And I didn't tell you too much about what those PhDs did, so you can imagine all the other interesting stories connected to this volcano. So thanks so much for listening and the questions in the chat so far.
Thank you very much, Michael. That was fascinating. So who has questions? Do we have? Oh, okay. I see a question from Mong Han.
Hi, Michael. Thank you for your talk. I really enjoy it. I guess I have a question about the conduit size and what set the size of that, and whether when you have a high or low mass eruption rate, is that going to influence the size of that? So how do you put that into the graph you were showing in your 2018 paper?
Yeah, that's a good question. You know, the conduit size has a huge effect on volcanic eruptions, and the speed of a fluid moving through a pathway scales like the diameter squared. So the flux is going to go like the diameter to the 4th power. And the conduit is essentially a dike or a crack. And so it's going to be coupled to the pressure driving magma to the surface. So real volcanic conduits are dynamic. They're going to evolve over time, and they're going to expand and contract. And so in practice, what we do, since these are unknowns, is we explore a range of conduit sizes spanning typically, say, 1 order of magnitude. And we hope that conclusions are not sensitive to unknowns in the conduit size. But in reality, conduits definitely change over time. Their geometry varies from the source up to the vent. And they change because of mechanical erosion as well. And if we look at the magmas that erupt, we often see a lot of materials transported, country rock that was transported by the erupted magma, presumably widening the conduit. That was a complete non-answer, except that it's a big unknown and has a huge effect. I think, are the hands up in order on my screen?
Yeah, I think so. I think Dan is next, Dan Lathrop.
Okay.
So nice talk, Michael. Good to see you remotely.
Thanks, Dan.
So I guess at the temperatures these are coming out, the water that then comes out of solution is a supercritical fluid. And maybe that doesn't matter. Maybe all that matters is really just the density of the water, or is there something? I know supercritical fluids are peculiar in other ways. Is it relevant?
Yeah, excellent question. I mean, as you go into the ocean, eventually you get deep enough that the fluids are supercritical. So that will have, of course, an effect on their density and thermodynamic properties. Here, the vent was 900 meters below the ocean surface. So actually, water is not supercritical at that point. It would be a true vapor. In the numerical simulations we do and the models for what happens to the pieces of pumice, we do use the equation of state for water. So all these details I don't keep track of. Ben's hand went up next, and that'll be the 3rd Berkeley graduate in a row.
Yay. I have 2 quick questions, I think. One is the float duration seemed like it would be strongly affected by wave action at the surface, and I'm wondering if you have estimates on that. And the second question is, are there hydroacoustic recordings of the eruptions themselves akin to the infrasound recordings we have for subaerial eruptions?
Yeah, let's answer those in order. So in our flotation experiments in the lab, we do not make waves. In a different set of experiments, we did experiments with waves, Martin Utzler, and he was interested in how the pieces of pumice abrade, because that wave action causes them to slide past each other. And so the waves will definitely affect their shape and the erosion, which also will affect how long they float. So I can't answer the question whether waves will provide another pathway for them to get wet. We did get permission to look at Navy data to try and the value of the hydroacoustic signals would be to document when exactly the eruption began and when it ended, without relying on the sparse satellite information, and hopefully maybe get additional insights into those 14 lava flows and lava domes, and whether there was any precursory volcanic activity before the raft formed. And I think this would be a great project for an ambitious student who knows how to work with hydroacoustic data, because at least we know where the volcano is, and we know roughly the time period to be looking at. Laurent?
Hey, good to see you remotely here. I have also two small questions. The first one's a bit related to what Ved was talking about. I'm kind of curious about the rate at which the abrasion happens. And I guess I'm trying to reconcile all of the different sizes, because you have the big pumice should float, but then you find them also quite a bit at the bottom. So I'm wondering if you have like the possibility of stratification about the deposits, at least close to the vents, where they may be originally breaking down pretty quickly, and whether we would see, kind of big pumice covered with small ones, or maybe it's the other way around. I'm a little bit not sure which way it will go. And my second question is just as a curiosity, anything would prevent that from happening in a very deep lake, like say on Crater Lake in Oregon, for example?
Yeah, let's go backwards. So eruptions like this have happened at Lake Taupo that created floating pieces of pumice, and very big ones, in fact. And so I think there's nothing special about deep submarine and very deep lakes. And this includes on other planets, for example. So to provide some context for the first question, volcanologists rely a lot on sizes of fragments and size distributions to get a window into process. And so here you can think about all the different processes that are recorded by the size, including what caused fragmentation, as well as transport and abrasion. And in the proximal setting, we mostly see just giant pumice. And then on top, there's also other ash layers and something called a lapilli layer from different phases of other parts of the eruption sequence. Associated with these lava domes, for example, there was probably weak ash venting that created some of these units. And so why don't we see smaller pieces of pumice? Because they were not able to sink in the proximal setting, and they weren't able to get abraded to develop that small size. Let me grab a bag of pumice. So this is a bag of pumice from a beach in New Zealand. You can get a sense of their size. These are not bigger than a meter. But by the time you get to New Zealand, you've been transported at least a couple thousand kilometers. And they could have broken up for mechanical reasons. And then they've been abraded to develop that smaller size. But the model I showed you is, if you think of it as a hypothesis, for pumice to reach the ocean surface, we said they have to be bigger than about a meter. So these started their lifetime bigger than about a meter. I should point out that that model did not account for the fact that you may be heating up the ocean, and there may be a mixture of steam plus liquid water in that eruption column, and that would slow the rate of ingestion.
Yeah, I mean, when you got there in the first place, right? I mean, or maybe not necessarily in this particular example, but in some other pumice raft, I mean, then you would expect to only see very large ones. And if you come later, you wouldn't see them anymore.
Yeah, right. All the smaller pieces of pumice, most of the mass went into the raft and disappeared.
Right.
So if you were a geologist coming to this volcano and looking at the stratigraphy and tried to estimate the size of this eruption, you would be off by more than an order of magnitude. The volume of the pumice that make up the field of giant pumice is more than an order of magnitude smaller than the volume in the raft. And so reconstructing the history of submarine volcanoes suffers from most of the material being deposited globally.
Yeah. Thanks. Interesting work.
Megan, I'm not keeping track of whose hands went up next, but I think I saw Karen and you, and I'm not sure if Ved has yet another question or is he didn't take his hand down.
I don't know how to take my hand down.
Okay, Karen, did you want to go next?
Sure. So yeah, my question is about essentially whether you can see floating rafts from major terrestrial eruptions and model them going down river systems. I guess the only one that comes to mind is the Yellowstone caldera and the wide Missouri River that's pretty close to it. That's the only scenario that I can envision. I guess someone's in Iceland as well, maybe. But anyway, can you get large enough particles? I mean, you get fairly big pumice particles ejected from, let's say, Mount St. Helens, and it's sitting there on the pumice plain. But a much larger eruption might provide enough ejecta that go a little bit further, and then rafts can go down rivers. Can the same approach be used to modeling that? Different parameters, I realize, but
yeah, I suppose in principle, I mean, in places in a on land setting, the deposits from the pyroclastic density currents and the fall deposits can be quite thick, and they would probably choke off rivers.
Yeah.
This is, of course, how we make lahars. And the Philippines provided a great opportunity to study that remobilization and transport, and it continues to, the pumice that was deposited continues to be
and we don't see much of that floating. I mean, it is going as debris flows and things like that, but we don't see much of it floating. I was just wondering for a much larger explosive eruption, like, you know, one of the way earlier mega Mount Yellowstone eruptions, whether you could get significant rafts of pumice. I don't know. I just wondering, should be looking for it in the Gulf of Mexico or something.
Yeah, good question. Because as long as you float long enough and get into the ocean, then you can be transported by those ocean currents.
Yeah. Right. Thank you.
Megan?
Yeah, I had a question about, you related mass eruption rate to gas loss, where, you know, if you have higher mass eruption rate, you retain more of your vapor. I understand how that works in mafic systems where the bubbles are able to rise up through the magma. How does this work in silicic systems?
Yeah, I forgot to explain the core physics behind that, didn't I? So in silicic systems, the viscosity of the melt is so high, the bubbles do not move with respect to the liquid. They stay fully coupled. And so if the mass eruption rate is high and you're moving through the conduit quickly, there's less time to lose gas through porous flow. And so the lower the mass eruption rate is, the more time you have to lose gas during ascent. And so in the end, there are two quantities that determine the loss of gas during ascent. One is the time you have, and the second is the pressure difference driving gas out of the conduit. And Philip had his hand up.
Thanks very much for that. That was very stimulating. Your contrast between St. Helens and some of the pumices from the seafloor reminded me of a talk I saw 30 years ago at a geothermal energy conference by Fraser Goff. And he had looked at gases that came off of Mount St. Helens. And if I remember correctly, the magmatic gas signature was lost, essentially contaminated by meteoric water after just several weeks. You have 5 experiments behind you. And I would assume that in the interior of those pumices, there are fluids or gases trapped that have a magmatic signature. Is it realistic? Has anybody thought about going in and extracting those fluids to see what they are and what the isotopic composition is and the trace element signatures?
Yeah, absolutely. So we collected a huge amount of rock, including samples from the seafloor. And in the little pieces of pumice that are recovered from the seafloor, so these never would have reached the ocean surface probably, you do see in the X-ray computed microtomography images, some of the bubbles have filled up with ocean water and some are still filled with gas. And so those would be the primary magmatic gases. And Kenny Beefus has those right now, so he's going to make CO2 measurements on them. Be interesting to look at the noble gases that are present inside those bubbles too, because it should be a pristine sample of magmatic gas.
Mm-hmm.
Michael, there are a couple more questions in the chat.
Shoot, I was just looking for hands going up and not ignoring the chat completely. Sorry about that. Yeah, so I think it's maybe 20% of volcanic arcs are submarine. So roughly 20, presumably, if the mass flux at submarine arcs and on land arcs is roughly the same. About 20% of the volume that erupts on land should be erupting in the ocean. And the fact that we know of on average of one submarine eruption per year means that there are probably other submarine eruptions happening that we do not know about. And we don't know about them because we don't see them, right? You have to be big enough to reach the ocean surface, and you have to make a seismic signal that is recognizable and that you can separate from that background seismicity that happens everywhere in volcanic arcs all the time. And so Ved's comment about using hydroacoustic data may be the best way for monitoring submarine volcanism, which is to identify signals that are distinct to submarine eruptions and use those and track their sources. And what sets the distribution of bubble sizes and how does it affect the sinking time? So the size of bubbles ultimately is going to be controlled by the number of bubbles per unit volume, and then solubility, which depends on pressure. So if you know the number of bubbles per unit volume and you know the solubility, you can determine the average bubble size. So then the question becomes, well, what controls the number of bubbles per unit volume? Nucleation rate is controlled by decompression rate plus nuclei on which bubbles can nucleate. So subject of very active research, and there are lots of empirical scalings. And so as an aside in the modeling, I just use what we measure for this particular eruption rather than trying to compute it based on theory.
Perfect. Thank you so much. We better let you get to your class.
Yeah, right. Excellent. I get to teach in 1 minute. And I'm teaching a class called URGE, Unlearning Racism in Geoscience. And I hope there's a Maryland pod of URGE. If not, URGE has great resources online. And again, Megan, thanks so much for giving me the chance to visit today. And
thank you. This was a lot of fun. And thanks for finding time for meetings as well and all our questions.
always good to